Auzu billahi minash shaitani rajim. Bismillahir Rahmanir Rahim. My name is Sanaullah and my CMS ID is 031170012. And I have assigned the presentation of VLSI. The topic is Metallization by Dr. Saeed Ahmed Khan. First of all, introduction. What is metallization? Metallization, fabrication of circuit included two parts, the active and passive part. This is called the front end of the line, and middle system, back end of the line. Basically, metallization is the final step in the wafer fabrication sequence. Metallization is the process by which the components of the ICs are interconnected by aluminum conductor. And there are other uses of metallization as to to produce the metallized area called bonding pads around the periphery of the chips, to produce metallized area for the bonding of wires leads from the package to the chips. Now, objectives. List of the component of a material for use is a chip of surface conductor. Draw cross section of single and two layer metal schemes. Introduce three material used in metallization. All about sputtering, evaporation, and CVD methods. These are the methods. Describe the principle and operation of vacuum pumps. Now, first of all, conductor single level metal. Now these are actually the metal surfaces, like first of all, one is the wafer with dope region, the second one is the patterning open contact, and the third layer is the conductive layer. There's one this is our to 15,000 angstrom sputtering CVD operation. These are the three single level metal. Now, feature of metal system: convenient current and connection and addition between SiO2 and metal, purification, prevent against unwelcome rust, and A level without hole. These are the feature of metal system. And now, conductors, multi-level metal schemes, like increasing the chip density, decreasing the available space on the wafer for wiring. Like if you increase the chip density, then obviously the space of the wafer wiring will be decreased. If you see in the figure, advanced multi-level logic device, there are P level and N level below and above. There are metal layers which connected via vias, and it is connected to outside the world, like transistors connected outside the world with metal. These are different layer of metal 1, metal 2, and so on. Now, front end versus back end. If you see in the figure, there are N and P level. Like in front end, there are drain, source, and gate, and the back end there will be metal contacts and vias, like global interconnects. So these both are connected, like one is back end and the second is the front end. Now, backend technology. Backend technology, fabrication of interconnect and dielectric that electricity isolate them. All this structure was simple by today's standards. And more metal interconnects level increase circuit functionality and speed. Interconnect are separated onto local interconnects, like polysilicon, silicides, and TIN, like titanium, and those. And intermediates, global interconnect, like copper or aluminum. These both are conductor used for intermediate global interconnection. And back-end process is becoming more important. Larger fabrication of total structure and processing started to demand total speed of circuit. Now, conductor multi-level metal schemes, like for example, creating a CMOS inverter, the wafer, like there are thin oxide anvil, and above this we have creating a CMOS inverter. Like this example I taken from Google. related to multi-level metal scheme. Like there are a multi-level metal scheme, like one is above other. There are many metal layers which are connected with each other. Now there actually a CMOS substrate. Here if we see here is a one N channel and the second one is the P channel. If we assume, if we suppose and imagine the diagram that we discussed in the class, like one is N channel, the second is P channel, the field oxide, the this one is the lost boundary of the front end side. And now this is the barrier, like we connected here layer up to layer to connect our transistor with the global. And this is the dielectric layer, this is the another layer, intermetallic dielectric layer. Now plug opening, like there are plug opening, we used lithography and exposure and other photoresist, and we dig these places like plug hole vias and plug filling. Now we put some material like SiO2, or like we studied, and like we studied in previous lectures. Here we put SiO2. Now first metal layer, we have connect about it. First metal, this one is the first metal layer. And now this is the second IMD layer. Above the metal layer we have put another IMD like this one. Like we connect this here, we have created a hole, and this like the same here we are also creating these places, and put the SiO2 there too. And then again we will put another metal layer, like here a layer of metal will made above and above, like we connect our transistor to the global. Like if you see here is another third IMD layer, like this one is a third IMD layer. Above metal there will be IMD layer. And again here is a plug opening, and then again we feel that ready for another connection, like we feel it and ready for another connection. Like this is the whole summary of the metals. Like here is plug metal 1, metal 2, and IMD layer. These are IMD layer, like the brownish color. These are the IMD layer, and the blue color is which we fill the area. This is the blue color, and these are the multi metal system cross section. Now it is actually the image of the actual image of the metal layer, like the below in is this transistor, and above there is metal 1, metal 2, metal 3, and up to metal 6. There are these all are the metals. Now if we talk about the conductivity, like metal bulk resistance, like silver has the bulk resistivity of silver is 1.6, and copper is 1.7, gold is 2.2, aluminum is 2.8, and tungsten is 5.3, and molybdenum as 5.3. Now conductor aluminum. Now we will talk about the. Now, from an electrical conduction standpoint, aluminum is less conductive than copper and gold. Prior to the development of VLSI level, VLSI level circuit, the primary metallization material was pure aluminum. Like we compare below the aluminum and copper, it's with respect to resistance and melting point. Aluminum has resistance 2.7 micro ohm centimeter, and copper is 1.7 micro ohm centimeter, while aluminum melting point is less than the copper. The aluminum boiling melting point is 660 degrees centigrade, while copper has 1084 degrees centigrade. Why we choose aluminum? There are different things. That's why we choose aluminum. The thickness is the thickness of aluminum is about 1 micrometer, and the width of the about 2 to 25 micrometer. The use of aluminum offer the following advantages, like in early technologies, and if we go back, then we use aluminum because it has the properties like it has an relatively good conductivity. It is easy to deposit into the water by vacuum evaporation. The other properties, it has good adherence to the silicon dioxide surface. Aluminium form low resistance. So these were the properties. That's why always in previous baking technology we used aluminium as a conductor. Now here copper, if we use direct replacement for aluminium, has a high contact resistance. Like copper, if we as a direct replacement for aluminium, has a contact resistance. Aluminium emerge as the preferred metal because these are the properties, and that's why aluminum emerges the preferred metal, because it has low enough resistivity, 2.7, like I discussed previously, 2.7 ohm, as compared to copper, and good current carrying density. Number two, it has a superior addition to silicon dioxide, and is available in high purity, has a natural low contact resistance with silicon, is relatively easy to pattern with the conventional photolithography processes. Aluminium sources are purified to 5 to 6 inches purity, like 1999.9. And now problem in aluminium, like aluminum and silicon lie at 577 degree centigrade, and I mean 577 degree centigrade. Aluminum and silicon lie mid start at 455 degree centigrade, the convenient temperature for a good junction. But aluminum spikes punctuate the dope junction and make short contact. Like I discussed in the class also, the aluminum when it is doped, and make spikes like shown in the figure, like it goes to silicon substrate a little bit, like if you see in the figure, there are spikes. Now aluminum, it is used for contact and interconnect reasonable resistivity, like I discussed previously. That is the same thing I and little bit yeah, like adheres well to silicon and SiO2, good contact to dope silicon, and interconnect with SiO2 for Al2O3, aluminum trioxide, and will facilitate contact through the internet oxide barrier, inherent oxide barrier layer that naturally grow on silicon, and can reduce other oxides, can be etched and deposit easily. Like aluminum, these are the property of aluminum in concern. Contact resistant cell size and spiking or migration through a shallow junction emitter of NPN metal, migration in region of high current more. Now this is the actual photo of the spikes, like in if we see here, there is the silicon substrate, like the last one is the silicon and PN junction. So here actually the spikes, if you see here, the black area is the spike, like I discussed later earlier. So this is the actual photo of aluminum, and this is the drawbacks. This is the drawbacks of aluminum, and it creates spikes in silicon substrate. Now there are two solution. The first one is the barrier layer visa and multi-level schematic, like tungsten W and tungsten N are used like perimetal, and the second one is the aluminum with 1 to 2% silicon. That is not reliable actually. Now the best solution is that aluminum alloy with 0.5 to 4% and copper, or 0.1 to 0.5% titanium. Aluminum alloy with silicon and copper can use to solve both problems. Whatever the problem is, we can easily solve with the alloy of silicon and copper. These are the solution to the problems. Now conductors, aluminum, overall effectiveness of a metal system is governed by the resistivity, length, thickness, and total contact resistance of all the metal wafer interconnect. In a simple aluminum system, there are two contacts, the silicon aluminum interconnect and the aluminum interconnect wires. and the VLSI circuit with multi-level metal layer, barrier layer, flux file, polysilicon gate and conductor, and other intermediate conductivity layer, and the number of connection becomes very large. The addition all the individual contact resistance can dominate the conductivity of the metal system. Like here. Here are the three methods which I discussed earlier, like filament evaporate, and second one is the electric beam evaporation, sputtering. These are the method. These are also the methods of the metallization, uh, which we discuss in the class 2. So that's all about my presentation of metallization, and thank you so much.